Beyond eccentricity, orbits may have the same eccentricity, but may be different sizes. There must be a Keplerian element which describes the size of an orbit. So the semi-major axis. The semi-major axis describes the size of the ellipse. It is half of the largest diameter of the major axis of the orbit. So again, here's our major axis, our semi-minor axis on A here is going to be half of that. So that's going to be the center of the ellipse. And the semi-major axis originates from the center of the orbit, but we are located on Earth. And so this makes the semi-major axis difficult for us to visualize from our reference point. So here's some important points to know about orbits. So an apogee defines the point that the point of orbit that's farthest away from Earth, and then the perigee is just the opposite of that. That's the point where it's closest to Earth, and then the apogee altitude is the distance between the surface of the Earth and the apogee, and then the same is true for the perigee, the distance from the surface of the Earth to the perigee as well. And so as a little kind of fun side note, G suffix means Earth. For example, apoapsis and periapsis. Apogee, perigee, and circular orbits. So for a circular orbit, the apogee altitude is equal to the perigee altitude, which kind of makes sense. And so in a circular orbit, apogee altitude and perigee altitude are the same. Perfectly circular orbit has neither an apogee nor a perigee and is undefined. Perfectly circular orbits cannot be achieved just because, of all the other variables that kind of come into play, with different gravitational pulls and the Earth not being a perfect sphere, so on and so forth. Generally, circular orbits are described by their altitude. A semi-major axis is rarely used to describe circular orbits. So here, things seem to get a little bit more complicated, and we'll never go into some of these equations right here, but we'll talk about this here just for a moment so you can kind of see how this works. But semi-major axis is the only orbital parameter that determines the orbital period. So this is translated as Kepler's third law. So the square of the period of a planet is proportional to the cube of its mean distance from the sun. So let's actually take a look at this for a second. And so we have these five dots right here that are going to race around the sun. And which one do you think will finish first? Well, let's click and see. And so you'll notice as it spins around that the orbit closest to Earth is going to spin a lot faster than the orbits that are farther away from the Earth, which would kind of make sense. Semi-major axis. So these orbits all have the same major axis, but their eccentricities and their orientations around the Earth are different. So you'll notice that these will all start out at the same time. And so what we want to do is we want to observe the orbital periods. Okay. So their orientations are different, and their distance from the center of the Earth is changed as well. But you'll notice that at some point it does still take the same amount of time for each one to orbit. So describing the orientation of orbit in space. So orbits may have identical sizes and shapes, yet they can vary in their orientation in space. So these are the three additional Keplerian elements that define this orientation. So we have inclination, we have the right ascension of the ascending node, and then we have the argument of perigee. I'll move back here. And so you can kind of see how some of this works. Here we have different inclinations. The right ascension of the ascending node, which we'll talk more about, and then the argument of perigee, which we'll kind of go into more detail as well. But let's actually start with inclination. So inclination is the angle between Earth's equatorial plane and the plane of orbit. It describes the tilt of the orbit. So here you can see that these different colors again represent the different angles that these are at, using Earth's equatorial plane right here. And so which satellite will complete the orbit first? Well, it looks like they're all the same. You'll notice that they all kind of hit this point at the same time. So it doesn't really matter as far as its inclination whether or not it will change its speed. That does it for this video. If you have any questions about anything as you complete the guided notes, as always, be sure to ask. All right, good luck.